Welcome to The Explainer. Today we're going to unravel a pretty wild paradox right at the heart of modern AI. I want you to imagine an algorithm that doesn't actually learn, at least not in the way we usually think about it. We're talking zero training time, absolutely no complex parameters to optimize, and no massive neural pathways. Yet this deceptively simple algorithm is quietly powering some of the absolute most advanced systems we use every single day. It's called K-nearest neighbors, or KNN, and today we are going to figure out exactly how this beautifully simple secret works.
Okay, let's dive into this. Here's our roadmap for today. We'll start with the simplest AI algorithm, look at how nearest neighbors vote, and define mathematical distance. Then we'll tackle lazy versus eager learning, the curse of dimensionality, and wrap up with speeding up the search.
All right, let's kick things off with Section 1, the simplest AI algorithm.
The entire core philosophy of KNN can be captured in just one phrase. Store everything. Predicts by looking at your neighbors. Seriously, that's it. Unlike other machine learning models that spend days or literally weeks crunching data to learn abstract parameters, KNN just memorizes the data. It stores the entire training set, skips the training phase completely, and relies purely on the intuitive idea that similar things exist close to each other. Now, you might be thinking this sounds a bit basic, but it absolutely blew my mind to realize this algorithm is everywhere in modern AI. It's just operating under different names and at massive scales. When you see vector databases doing huge searches over embeddings, or LLMs using retrieval augmented generation RAG to fetch the exact document they need, or even when your streaming app recommends a movie, that is KNN in action. Finding similar users, items, or texts is exactly what this was built to do.
Moving right along to Section 2, how nearest neighbors vote.
So how does this zero training magic actually happen? It's a brilliantly simple four-step process. Just picture yourself standing in a room full of people, and you need to make a decision. Step 1, you measure your exact physical distance to every single person in that room. Step 2, you sort everyone based on who is closest to you. Step 3, you take the K closest people, let's say the 5 people standing right next to you. And finally, Step 4, you just ask those 5 people for their opinion, and you take a vote, or, average their answers if you're looking for a number. That is the whole algorithm. No gradient descent, no fitting, just pure logic. So for classification tasks, that final step relies on a simple majority vote. You literally just count which category is the most common among your K-nearest neighbors. Quick pro tip though, if you're doing binary classification, like deciding between yes or no, always choose an odd number for K. If you use K equals 5, you'll always have a clear winner, and you completely avoid any annoying ties. Now here's where it gets really fascinating. The delicate balance of this entire system, the bias-variance trade-off, is controlled by tweaking just one single hyperparameter, the number K. If K is 1, the model just copies the single closest point. It follows every little blip in the data, meaning it overfits wildly. A small k, like 3 or 5, beautifully captures complex, intricate boundaries. Making K really large smooths those boundaries out, which is great for ignoring noise. But if you make K equal to n, meaning your entire dataset, it just predicts the majority class for every single point, completely ignoring local nuances. Tweaking this one number literally changes the model's entire reality.
Which brings us to Section 3, defining mathematical distance.
You see, changing how we measure distance completely changes who our neighbors actually are. If you have standard numeric data on a similar scale, you'll use the default L2 Euclidean distance, just your standard straight-line distance. But if your data has wild outliers, you might want L1 Manhattan distance because it doesn't square the differences, making it way more robust. And for modern AI dealing with text embeddings, we absolutely have to use cosine distance. With text, the size or magnitude of the vector is just noise. The true meaning is found in the direction it's pointing. Oh, and there's also a fantastic upgrade to the standard algorithm called distance-weighted KNN. I mean, think about it. A neighbor standing right next to you should probably have way more influence on your decision than a neighbor standing all the way across the room, right? By giving closer neighbors a heavier vote, the algorithm actually becomes way less sensitive to choosing the perfect K number. Those faraway neighbors naturally just lose their voting power.
Let's pivot a bit for Section 4, lazy versus eager learning.
This is a massive paradigm shift in computer science. Most models out there, like neural networks, are what we call eager learners. They do incredibly heavy computation up front during training to build these compact parameters. So when you ask them a question later, boom, the prediction is lightning fast. KNN is the exact opposite. It's a lazy learner.
It does zero work up front. It just stores the data and chills. But when you finally ask it a query, it has to do all the heavy lifting right then and there, measuring the distance to every single point.
Now for a bit of a reality check. Section 5. The Curse of Dimensionality.
Up until now, we've been picturing data points on a flat 2D graph, or maybe a 3D room. But what actually happens to the whole concept of a nearest neighbor when you scale up to hundreds or even thousands of features? What happens in high-dimensional space?
What happens is basically a mathematical failure. As dimensionality increases, and this is wild, distances actually converge. The ratio between the furthest point and the closest point approaches 1. Essentially, in high dimensions, every single point becomes equally far away from you. Plus, the volume of the space totally explodes, and the vast majority of it gets concentrated in the corners. When everyone is equally far away, the very concept of a nearest neighbor just becomes completely meaningless.
50. That is kind of the magic number here. Beyond roughly 20 to 50 features, standard CAN-N starts to severely degrade. So, if you're dealing with high-dimensional data, you absolutely have to use dimensionality reduction techniques first, stuff like PCA or UMAP, to compress that data down before you can let the neighbors vote.
All right, final stretch. Section 6, speeding up the search.
So, the glaring flaw in being a lazy learner is the brute force search. If you literally have to compute the distance from your query to every single training point in a massive database, that is going to take forever. It's perfectly exact, sure, but it is dreadfully slow and totally impractical for the real world.
But computer scientists are clever, and to avoid checking every point, we can use structures that prune the search space. KD trees, for example, recursively split the space into boxes. If you know your closest neighbor is in your current box, you don't even bother checking the boxes on the other side of the graph. Ball trees do something similar but use nested hyperspheres, which actually works a lot better for moderate dimensions. By organizing the data up front, we save massive amounts of time.
But what if we're talking about millions or billions of points? At those truly massive scales, we use approximate nearest neighbor algorithms, or ANN. Tools like FAST intentionally trade away the absolute guarantee of finding the perfect closest neighbor, all in exchange for finding a good enough neighbor at absolutely blinding speeds. That little approximation is the hidden engine keeping modern AI fast and responsive.
Which leaves us with this final thought. The next time an AI instantly recommends the perfect article or the exact right product, ask yourself, is the machine really thinking in some complex, abstract way? Or is it simply doing what this beautiful, parameter-free algorithm has done for decades, just looking around the room and asking its nearest neighbors? Thanks for joining me on this explainer. I really hope this helps you appreciate the hidden simplicity powering our everyday tech. Keep learning, and I'll catch you next time.